Okay, welcome. We're going to go ahead and talk about how to find the centroid of a complex shape by breaking it down into smaller shapes. So this shape I have right here, not that complicated, but hopefully you can see that this trapezoid, I did intend to make these right angles, at least to verify that they are, can be broken into a rectangle and a right triangle. Two shapes that we knew how to find the centroid of fairly easily. Okay, so what's going to happen is there's going to be a centroid for the rectangle approximately here, and we know there's going to be a centroid for the right triangle, approximately here. But we somehow need to get those two to be, I loosely use the word average, kind of average together, more like a weighted average, to figure out where is the centroid for the overall shape. Okay, and there's a formula to do that, but first, what we need to do is find the centroids of these two individual shapes. Okay? And so we'll call the rectangle shape 1. And for a rectangle, we just find half, basically the base, and half the height. So if we come half of 7, kind of right here, and half of the 5, kind of right here, we get the centroid right here. Okay? And we can mark those distances. Okay? We can mark the distances on the rectangle, right, is going to be 3.5 over of the 7, half of the 7, and it's going to be halfway up. Okay, so I am going to mark it from the side here. Okay, then you come over to the right triangle, and we had a rule that said from the right angle, you can go 1/3 of the length along each leg. Well, we need to know how long the leg is. This was 7 down below. The overall length here was 7. That's going to come in handy to make sure we know that. With the overall above on 10, that means it's 7 to here. So 7 plus what makes 10, this is going to be 3 units right here. And so to find the centroid of the triangle, we need to come 1/3 of the length of this leg. So 1/3 of 3 is 1 unit. So kind of think of breaking this into thirds. It's going to be along here. Okay, and then along this leg, which was 5 units, we need to come 1/3 of the way. Now I'm just kind of eyeballing thirds to illustrate, so it's going to be approximately right here. Okay, and then this distance right here is 5/3. I just divided the leg's length by 3 to get 1/3 of that length. Okay, now we'll go over the formula here in a second, but what you need to know is that you're going to need the coordinates of these two centroids, and you're going to need the areas of the shapes. We're going to put it into a format and kind of format it to help us out. But let's go ahead and record. We'll call in blue, I'll keep it color coded. So we've got the triangle, and we're going to get that, and then the rectangle will be called X1 and Y1. Okay, now these ordered pairs, this is an important thing. The ordered pairs representing these centroids have to be written with respect to the same point. Basically, you have to establish an origin, a 0, 0, which I haven't done anywhere on the paper yet, officially. So I'm going to make this bottom left corner, right there, I'm going to make that 0, 0. So basically, this is my y-axis, and this is my x-axis. Okay. When you record these ordered pairs, they have to have their origin in common. Well, the rectangle, we found those distances from that corner, so that's easy. We're just going to come over 3.5. That is, if that's the origin, that's right 3.5. And then we went up 2.5. Okay. For the triangle, the centroid, it's a little different. We're going to have to figure out these distances. We had this distance of 1. We've traveled to the right here, right from the corner here of the triangle, the right angle. So that's not from the origin. Well, thankfully, this is a nice length for this one. We came over, if we come from here, we'd come over 7, and then another unit, right? So if you think of trying to find this distance right here, that would be 8. So that's the x-coordinate for the centroid of the triangle. Now the y-coordinate, what we need is, again, from the origin, we need this height right here. And that's what we're looking for up to here. Well, the 5/3 is this distance from the top down to this point. That was 5/3. Well, we know that 5/3 and this y-coordinate have to add up to equal 5. So we could even write a little equation if you need, that the y-coordinate plus the 5/3 has to total 5 units. Okay, so really all we need to do is subtract 5/3 from the 5. All right, and 5/3 is 1 2/3, so 5 take away 1 2/3 is 3 1/3. I'm going to write it just as 3.3 with a line over 3.3 repeating. I'll just kind of keep a decimal format. Okay, so we need that, and then we're also going to need the areas. So the area of the rectangle is 7 times 5, base times height, 35. And the area of the triangle is 1/2 base times height, which was 1/2 of 3 times 5. That's 15. Half of 15 is 7.5. So we've got the area here of the rectangle, or sorry, the triangle, and we get the area of the rectangle right there. All right. Now I'm going to make a table. We have these two centroids right here, and we need to figure out how to merge them together to have kind of the weighted average of the centroids that account for, not just their locations, but how much mass they represent. Basically this is a section view of some beam, and we're trying to find the center of mass of the shape. So the centroid's going to be somewhere, we would imagine, between these. But this one represents a larger area, and this one represents a smaller area, and this one's not symmetrical either. So we kind of have to take that into account. You can't just average them, right? So hopefully you get that. So the formula, we're not going to worry about deriving the formula, looks like this. You repeat, in essence, the same process, but you do it once for the x-coordinates and once for the y-coordinates. So they write x bar equals, it's the quotient, okay, so we're going to divide, of the sum of the x-coordinates and their areas. Okay, so this is a product you're going to find, and for each instance, which is for each shape, you'll find the product of the coordinate and the area. And once you have those, you add them all up. You find the sum of those products. So that value is going to get divided by the sum of the areas of each shape. So for us, we only have two shapes. I made a little table, and we're going to just plug in what were the x-coordinates. So the I represents like basically a label to kind of say for each instance. And we have two instances, two shapes. Okay, so the x-coordinate of my rectangle in green was 3.5. I can keep it color-coded if that helps. And the area, well, I've got the green pen, was 35. And when we come over here to do the y-coordinates, the areas are going to be the same. That's going to be 35 as well. And the y-coordinate for that rectangle is 2.5. So we can go ahead and fill all that in. Then for the triangle, I had used blue. The x-coordinate was 8. The area of the triangle was 7.5. The y-coordinate was the 3.3, repeating, 3 1/3. And again, the area is the same, 7.5. Okay. So this y-coordinate here, the formula, it looks exactly the same. It's just a y instead of an x in there, so I'll write it out. We want the summation of the product of the y-coordinates and their areas divided by the sum of the areas. Okay? So now we got to just come through and find the products. Okay. Well, 3.5 times 35 is 122.5. That's just multiplying these two numbers here. Okay. And then I'll stick with the green for the y's. 2.5 times 35 is 87.5. And then for the triangle now, 8 times 7.5 is 60. And the 3 and the third times 7.5 is a nice 25. And then, if we remind ourselves of the formula, we're going to divide sums, the sum of these products, and divided by the sum of the areas. So we just need to find the sums. Well, if we add up the areas, it's 42.5, and that's going to be the same for the y's. It's just the same shape, same area, so I can fill that in. Okay. Then I need to add up these products. That's 182.5. And over here, we'll jump over here, that's 112.5. Okay. These tables would be great for you to lay out and keep all your work organized. The coordinates, the areas, and then your products. It's the areas and the products that are going to get summed. And let me just give you a friendly reminder that these coordinates were with respect to a common origin. They were not the distances from some reference point or corner of the shape. Okay, while we used this right angle, that corner, to kind of figure out where the centroid was, the coordinates are not expressed from this corner. They're expressed from what we established as our origin. So again, friendly reminder, establish your origin and make sure your coordinates, your x and y, are ordered pairs relative to that same origin for all shapes. Okay, so we've done all the hard work. The last thing is just to figure out where is that centroid. And so all we have to do is do our division. We'll get our x coordinate. So this is going to be the 182.5. Okay, this value is our numerator. And this value right here is our denominator. So 182.5 divided by the 42.5, and we get 4 approximately 29. Okay, I'm sure I rounded when I kind of calculated those. And then for the y coordinate of our centroid, again, we need these values here. First, it's the sum of the product, so that's our 112.5. And then that gets divided by the sum of just the areas. That's the 42.5. And we get approximately 2.65. So this is the centroid's location for the overall shape is 4.29, 2.65. And let's go ahead and mark that on the shape and try to approximate where it is. Well, if that was half, that was 3.5 there. If I can kind of establish approximately 1, 2, 3. I don't know. I'm trying to approximate where a whole unit would be. So 3.5. That would be 4.5. We're a little shy of 4.5. We'd be kind of, maybe along this line right here. And then our height of 2.65. Well, this was 2.5, so we're just slightly elevated from that. So just a loose approximation here. And this would be our centroid. Okay, and it makes sense that it is closer to the green because the green represented more mass. And it also makes sense that with that one maybe as a reference point, that how does the triangle affect it? Well, the triangle adds mass to the right, so it's bringing our centroid to the right. And the triangle, vertically speaking, doesn't have symmetry. There's more mass higher than there is down low, and so it should bring our centroid up slightly, which it did. Not a lot, but a little bit. Okay, so there you go. That is an example of finding the centroid of a shape, kind of a complex shape, that you decide to break into smaller, simpler shapes that you can find those centroids easier. So taking those centroids, using the areas of each region to kind of come up with the quote-unquote like a weighted average. All right?